So we are recording. Cool. So again, we're going to be looking at transformers, but today we'll be looking at three-phase connection. So we'll be talking about three-phase transformers. Cool. So to start off with, so we know that we generate in three-phase, and we know what that supply means. So in our day-to-day jobs, you guys may encounter three-phase supplies and equipment that operate at 400 volts rather than 230. What does that mean? How does 230 volts become 400 volts? And how is current flow affected by these values? So we need to talk about how the alternators generating the electricity energy are set up. Every alternator in our generation network is connected in what we call star configuration. Other countries such as USA refer to this as Y or WYE, but they are the same thing. Names both refer to the basic shape of the diagram when connected in a Y shape or a star. In this configuration, one end of each of the three windings are all joined together. The other ends are connected to the external circuit. In a balanced system, currents are able to flow from one phase winding to the load and return through the other. In an unbalanced system, then excess current that cannot flow via a phase is returned via the neutral conductor, which is connected in together with the three joined winding end. Also known as the neutral point, but you'll also sometimes hear it referred to as the star point. But that's mostly for when you're doing three-phase motors. Cool. So single phase connection to star supply. So consider the star configuration, like we can see here. Each phase winding is displaced at 120 degrees, which is why we talk about each phase being spaced 180 degrees out of phase from the other two. If a load is connected across one phase in the neutral, then effectively only the phase winding it is connected to will apply an EMF on the circuit. Current then flows from this winding through the load and returns to the other end of the winding via the neutral conductor. The magnitude and phase angle of the EMF is represented by phasor, which we can see here. We look at it from a mathematical phasor diagram point of view. There's only one phasor to consider, the blue phase winding. There's no angle associated in relation to the other phases because no other phase is connected. The magnitude of the phasor is something to consider, however. It can be seen here as 230 volts. As a side note, you can see that each diagram represents each winding to scale. Each is the same length because in reality, each winding within the alternator would be the same. Cool, and then we got polyphase connection to star supply. This is called a polyphase connection because poly implies more than one. We cannot say that there is a three-phase connection because technically in this diagram, there's only two phases connected. When a three-phase load is connected, the same principles apply. If a load is connected across the ends of two windings, then effectively these two windings are connected in series and the EMF is being generated in both of them is applied to the external circuit. It is almost as if one bigger winding is supplying the circuit. We cannot, however, simply add the EMF values to each winding together like we would with EMF supplied from two batteries because the two windings do not experience the same magnetic effect from the rotor at the same time. When the magnetic field is produced peak voltage in one winding, it is displaced from the other two, which has an effect on the overall EMF produced and must be resolved using phasor to determine the value. So by phasor, we're talking about the triangle diagram. The diagram here shows a quick resolution of the phasor involved. The length of the resultant phasor between the two tips of the supply phasors represents the magnitude of the voltage applied to the load. If you drew this out, you would find that it is to scale. Cool. So a simple explanation of the relationship between the two phases is that the resultant phasor is 1.73 times greater than each individual phase. As an easier way to remember this value, it is equivalent to the square root of 3. So this is nice and easy because the three-phase calculation requires the square root of 3 to be factored. These two terms we must use. There are two terms we must use to identify the type of voltage measured we're talking in these situations. So phase voltage, so the voltage measured directly across one winding. This can be written as VPH, and line voltage, the voltage measured across or between two windings. This can be written as VL. So the way I like to remember this is voltage phase is one phase, so single phase. You're only measuring across one phase. And line voltage is from line to line, so from line 1 to line 2. As mentioned before, the relationship between the two is square 3, and VL is always greater than V phase in star. Therefore, we can adapt the following formula, and Y or star voltage line equals square root of 3 times voltage phase. Always remember to this thing of the installations we work on. All three-phase installations have the following characteristics. All neutrals are joined together at the main neutral bar. There are two standard voltage levels, 400 and 230. This means that the installation is connected in star. This cannot be achieved using the other connection method we will look at. This prompts us to remember the formula above. All you have to do is remember the relationship factor, square 3. Cool. So phase angle, so phase displacement must also be taken into account. In three-phase configuration, the phase angle between VL and V phase can be observed as 30 degrees. This can easily be seen on the diagram between one phase and the line value. A simple justification of this fact is the geometry rules state that the internal angles of any triangle must add up to 180. When two phases are displaced at 120 degrees, that leaves 60 degrees to be split across the other angles. And so long as the magnitudes of each phase are equal, then the phase displacement between each phase and the line voltage will also be equal. So this leaves 30 degrees for each angle. Cool. So this explanation is a simplified one for ease of remembering the relationship between phase and line values. Remember that this phasor diagram represents all values at their max at the same time. If a time-lapse phasor diagram was used, it would show all three phases interacting with the line voltage value. That would be constantly moving as the phase values rise and fall. So we can see this in the animation below. The resultant phase is the black line, and then you've got the phase A, B, and C for the red, green instead of white, and then blue. All good. You'll be able to watch the video afterwards. We haven't gotten too deep into the weeds yet. So we have to remember in star configuration, voltage line equals the square root of 3 times voltage phase. Should be PH, not PL there. How can we, here we can see how each voltage is measured, phase to phase in dark blue and phase to neutral in purple. As discussed before, we can see that between phase and neutral, there is 230 volts, and between phases is 400, which is equal to 230 times square root of 3, which gives us 398.37, or for ease of remembering, 400 volts. Cool. Let's practice using the formula a little bit. Cool. So transformer is connected star-star and is a 45-to-1 step-down transformer, and the primary line voltage is 22.5. So first, we need to calculate the secondary line voltage. So we know that voltage primary over voltage secondary is equal to the number of primary turns over the number of secondary turns. So we know we can take the primary voltage and divide it by the number of primary. Cool. So the way we remember how to do this, one sec. Cool. So we've got our VP over VS is equal to NP over NS. And when we do this, it's not showing up very clear, is it? Hold on. Let's try using this. Cool. Cool. So you got your voltage primary over voltage secondary is equivalent to your number of primary turns over your number of secondary turns. Cool. So when we're dealing with fractions, we need to remember that we cross multiply. So you take your VP and times it by your NS, and you take your NP and you multiply it by your VS. So we don't know what our voltage secondary is. We know what our voltage primary is, and we know what the number of turns in the secondary and primary. So if we assume this is 1, we can multiply that by the number of primary and get 45. We know this is 1, so if we multiply it by voltage primary, we get 22.5 kV. So the resultant formula is voltage primary multiplied by number turns in the secondary divided by voltage secondary times the number of the primary. Because we don't have voltage secondary, we figure out that it's going to be 1 for now, and the number of primary turns is 45. So we end up with 2,500 because it's kVA. That's wrong. Okay, that's my bad. Someone want to do the math for me? 22,500 kVA divided by 45. Someone's taking the calculator out of this room. Yeah, actually, it should be 500 volts. For some reason, someone forgot to put the extra 2 in there. That's 22,500 divided by 45 does give 500 volts. And from there, we can calculate secondary phase voltage. So we know VL is equal to the square root of 3 times voltage phase. So therefore, we know that voltage line divided by the square root of 3 will give us our phase voltage. So that gives us 500 divided by the square root of 3, which gives us 288.68 volts. Does everyone see how this formula works? Anyone got any issues with it? I mean, obviously, other than someone putting the PowerPoint in the wrong spot. This guy. Yeah. Cool. Sweet. Cool. So we'll do it again. Cool. So transformer is connected star-star and it's a 5-1 step-down transformer. The primary line voltage is 10 kV. So again, we calculate the secondary line voltage. So we go VP equals VS over NP NS. So we know from this it's going to be 10,000 because it's kV divided by 5. It's 5 to 1 step down. So the secondary voltage is 2,000 volts or 2 kV. Then we can figure out the secondary phase voltage. VL equals the square root of 3 times V phase. We can rearrange again. VL over square root of 3 equals V phase. So 2,000 divided by the square root of 3 gives us 1154.7 volts or 1.155 kV, or you could round that to 1.16 kV, but that would be a little bit too rounded up for my liking. Cool, let's try it again, but this time, cool. So we have a transformer connected in star-star. It's a step-up transformer. the secondary line voltage is 8.5 kV. So we can calculate the primary line voltage. So VP equals VS. Again, rearrange the formula, we get 8,500 divided by 25, which gives us an input or primary voltage of 340 for our line. Then we can calculate the primary phase voltage. VL equals the square root of 3 times V phase, rearrange to VL over square root of 3 equals V phase, which gives us, 196.3 volts on our primary phase voltage. Okay, so that's how voltage works in a star transformer. But then what about our current? So Ohm's law has taught us that a load of a given impedance will cause a predictable amount of current to flow. However, depending on how the load is connected will depend on how much current will flow in the lines and through the load. So you may be asking, why would these values be different if the load impedance is always the same? So current flow is always dependent on the amount of force applied to the circuit, the voltage. Depending on the circuit configuration will depend on the voltage that is applied to the load. So we can also look at it in series parallel kind of situation. The load is in series with the phase winding and line conductor, so we'll receive maximum current. Once it has passed through the load and reaches the star point, it will split just as current does in a parallel circuit. But now, star configuration is easiest to remember the difference between phase current and line current. There is no difference. The current flowing in the phase winding of the supply is equal to the current that will flow in the line conductor and then through the load. The current labeled I phase here, as well as the supply winding, because in a transformer we would call the current flowing in the primary winding primary phase current. Cool. So we must keep in mind that the current draw is dictated by the load and the voltage applied. When red phase is at its peak, then the load connected to red phase will draw maximum current. The current is returned through the other two phases in the opposite direction because the EMF values of white and blue phase are equal to their negative half cycle. So in star, IL equals I phase. So in a star connection, current is always the same. So if you're asked for a delta star transformer, for example, and they give you the secondary line current, you know that the secondary phase current is going to be the same. Cool. So these are the transformer connections. We'll look at other transformer configurations, but to start with, we'll look at the basic star configuration. So we can look at transformer configuration diagrams in two types. One similar to what we have looked at up here, and an individual winding connection diagram. So we've got both down the bottom. So the one on the left is a representation of how they are connected. The windings are connected together. And then on the right, it looks more like a transformer we're used to seeing. So the windings facing off against each other. Okay, so now there's going to be a bit of a video about transformers. Yeah, hopefully it's not too boring.
Hello and welcome to this Electrical Principles training video. In this video, we're going to continue considering the subject of three-phase electricity. Now, in this video and in the subsequent video, we're going to look at loads that are connected in both star and delta. So you may have heard those expressions before in connection with three-phase, and they describe the two ways that we can connect up loads into a three-phase system. More specifically, in this video, we're going to define and describe the different voltages and the different currents that you find in three-phase systems. We're going to have a look at the relationships between those voltages and between those currents. So in this video, we're going to specifically look at a star-connected load. And if we just have a look at the rig that I've created behind us here, you can see that we've got 3 loads connected. Now, we're getting familiar with the idea that we can use resistors to represent the load. And in this case, this could be viewed as 3 heating loads. We could also start to consider this being the 3 windings of a 3-phase motor, or perhaps the 3 windings of a 3-phase transformer. These are all different ways that we can consider that. It gets a little bit more complicated when we start considering those. But the point is we've got 3 loads and they're connected to each other in star. Now, how do we know this is a star connection? Well, each load has 2 connections to it, electrically speaking. So you can see there's 2 connections there and there, and 2 connections there and there. One of those connections is connected to a supply line. So you can see here, this one is connected to the supply line coming along the bottom, and this one is connected to this supply line here. And the other end of each one of these loads is connected to each other and then to the neutral conductor. And that's what makes it a star connection. As you'll see in the next video, the delta connection looks very different. Now, it's important to bear in mind that when we look at a star connected load, we lay it out like this graphically, and I've laid this out like this as a demonstration piece. But actually, in reality, the 3 loads don't necessarily have to sit 120 degrees apart physically like they are here. If you look inside the windings of a transformer, you won't see the windings arrayed like this. When we had 3 heaters or 3 lamps plugged in to our 3-phase system in a previous video, they weren't laid out like this, but it does help us just to see the relationships between the voltages and the currents. So let's start thinking about the voltages and the currents inside these and the relationship between them. Now, in a 3-phase system, there are 2 kinds of voltage that we're interested in. There's what we call the line voltage, and there is what we call the phase voltage. Now, what we're going to do is we're going to give these definitions that make them work for a star-connected load and for a delta-connected load. So let's think about that first of all. What is the line voltage? Well, line voltage in a 3-phase system is the voltage that can be measured between any 2 supply lines. So we might measure it between L1 and L2, as we've got here. We might measure it between L1 and L3, or we might measure it between L2 and L3. Those are the 3 different ways that we can measure line voltage in a 3-phase system. Now, some of you may be watching this video and thinking, now I know how he's going to define phase voltage. The way I define phase voltage, it might seem a little bit odd to start with, but actually it helps us to understand how the same definition applies to star and delta. Because the way I define phase voltage is it is the voltage measured across the load. So it's the voltage across the load. Now, in a star-connected system, that's basically the same as measuring between any one of the lines and the neutral conductor. You can see that measuring between here and here will give us exactly the same value as measuring between here and here. So we'll think of phase voltage as being the voltage across the load. Now let's have a think about our line and phase current. So then we've got our 2 different kinds of current. We've got line current and we've got phase current. Now, at first glance, the definitions that I'm about to give here might seem pretty absurd for a star-connected load. You can see that they're going to be really useful when we get to the delta-connected load. So the line current is the current flowing through the supply line to the load. So it is the current flowing through the supply line. The phase current, the other kind of current in a 3-phase system, is the current that's actually flowing through the load. Now, what I've done on this rig is I've built in these little loops in the cable so that we can measure what they are. And actually, this really helps to demonstrate very easily what the relationship is going to be between the line current and the phase current in a star-connected system. So here we'll be able to measure our line current. Here we'll be able to measure the current that's flowing through the load, the phase current. So what we're going to do now is we're going to power up our star-connected load. We're going to measure the voltages, we're going to measure the currents, and then we're going to show the mathematical relationships between those voltages and currents. So what we're going to do now is we're going to connect up our star-connected load to a 3-phase supply, which is just off screen here. Now, we're working under controlled conditions, but obviously a 3-phase system is even more dangerous than a single-phase system, which is already pretty lethal. So please do not attempt to repeat this experiment in your own time. So what we're going to do, we'll power up So we've turned that on now. There's now electricity flowing into our three-phase load. And what we're going to do is we're going to, first of all, measure the line voltage. So that is the voltage between any two supply lines. I'm going to pick L1 and L2, and I'm going to measure the voltage between those. So using my beautiful Mega Avo 835, I'm going to set that to measure voltage, make sure that it's on AC, and then we're going to measure across here. Now I'm using these rather lovely Vargo connectors to make sure that I am absolutely safe there. I'm going to put these on at roughly the same time, so I have a live end waggling around. And then you can see that the voltage that we're measuring here is 426.3 volts we've got there. So 426.3 volts. So that is our line voltage for this system that we've got connected up. So what we're going to do now is we're going to measure our phase voltage, and we're going to see what that is. So remember, phase voltage is the voltage across the load. So in this case, we're just going to connect up across here. So if I can just get a connection onto here and a connection onto here in a safe fashion, you can see there we've got 246.8 volts. 246.8 volts. So hopefully those values are vaguely familiar to you, because of course on nominal voltage in the UK we say that three phase is 400 volts and we say that single phase is 230 volts. So we have those values pretty close. What we're going to do now is we're going to nip across to the whiteboard and we're going to have a look at how those two voltages are related to each other and what the kind of the number is that connects them. So you can see on the screen here, we've got our three-phase connected load. We've got our three resistors that are connected in star with each other.
That's basically just going over what we discussed before about the relationship between the phase voltage and the line voltage being square 3. So we'll just move on and we'll start talking about the delta configuration. Cool. So delta is the other possible configuration for three-phase systems. In terms of supply systems, delta configuration tends to be more prevalent in transmission and distribution networks. It is uncommon to see an alternator or the consumer side of a distribution side of a supply transformer configured in delta. We'll look into this into why shortly. A delta configuration can also be referred to as a mesh configuration, but either way they represent the same thing, symbolized by the Greek capital letter delta due to its appearance. So it's basically a triangle. This configuration, an end of each winding is connected to the end of another to form a triangle, hence the name and symbol. It is imperative that the right ends of each winding are connected correctly, so we must make sure that labeling is done correctly. Cool. So connection to a delta supply. So just like a star configuration, each phase is still 120 degrees displaced from one another. One key difference for a delta connection, though, is there is no capacity for a neutral conductor or connection. This means that any load connected to a delta configuration supply must be balanced. Motors are suited for this, as all three windings are the same impedance and draw the same current. In a balanced system, instantaneous voltages at any point will equal 0. A simple example of this is that when any one phase is at its peak, the other two will be in their negative half cycle value at half of the peak, after the peak. So when red phase is at 230 volts, white will be at negative 115 and blue will also be at negative 115. The sum of these voltages equals 0. This is always the case when impedance and current flow are equal. When they are not equal and there is an imbalance in the system, a potential will exist and cause circulating currents to flow. If the impedance of the circuit is low, excessive current can flow, causing excess heat and damage to the supply. Installations cannot be connected to a delta supply, as it cannot be guaranteed that loading will be balanced. So this is why at the consumer end, you always have a star or a delta star transformer, just because the loading, you can never guarantee that the loading will be balanced and you need that neutral return path. The same goes for the generation side because that neutral is your return point. So if the load on the generator is not balanced, and it might not be because the other end is not balanced, you need that neutral return path. Cool. So in delta configuration, we can see that the line conductors are tapped directly off of each end of any single winding. This means that the line voltage between conductors will be equal to the phase voltage across any one winding. This can be expressed in the following formula. So in delta, VL equals V phase. So in delta, voltage line and voltage phase are the same, which is the opposite of the delta, where current was the same at all times. So if you think of star as being series, so voltage is different in star, and delta being parallel, where voltage is always the same. So as mentioned before, it is more common to see transmission and distribution lines connected in delta. You'll notice this if you look up on top of a power line and see a set of 3 conductors. Although it is not guaranteed, it is very probable that they are configured in delta at high voltage level. You may see underneath them a set of 4 conductors. This will be a consumer supply which has been transformed to 230, 400 volts. The 4th conductor will be the neutral return conductor. So if you ever look at a street pole and you see levels of wires, if you see there's only one set and there's 3 wires, it means it's high voltage, stay away. If it's 4 wires, it's low voltage, but still don't mess with it because it is the distribution network. And the lineys are very, very titchy about us Sparkies working on their network. Unless, of course, we happen to be a linesman as well, which I'm not, so I don't touch it. Cool. So current, when a 3-phase load is connected in delta, it is almost as if the loads are connected in parallel with each other. If you look at the connection point, current flows into the load by a single conductor, but then splits in 2 when it flows through the individual loads. So just as we studied voltage in star, it is not quite the same as adding the values together, as they are 120 degrees displaced. However, just like in a basic circuit, like what we have previously studied, more current will flow in the supply conductor than split as it reaches the branches. Due to the phase displacement, the relationship between the current is flowing through the load, phase current IP, and the current flowing in the supply lines, line current IL, is 1.73 times, or a factor of square root of 3. So we can use the following formula to express the relationship. In delta, IL is equal to the square root of 3 times I phase. Cool. So let's have a go at this formula. Cool. So transformer is connected delta-delta and is a 45-to-1 step down transformer. The secondary line current is 22.5 amps. So first, we look at the primary line current. Cool. So when we're talking about the current, we must remember the formula that we've studied previously. So voltage primary over voltage secondary is equivalent to N primary over N secondary, which is equal to I secondary over I primary. So we know when we talk about circuitry in terms of parallel and series, voltage and current are always the opposite of each other. So the voltage primary is equal to the over voltage secondary number primary. Cool. So now that we know this, we can take our I secondary and our primary next to our NP over NS. Cool. So we know we need to cross multiply. So to rearrange this formula, one sec. We know that I secondary times number primary is equal to I No, I made a mistake there. I secondary multiplied by number secondary over I primary times number turns primary. Cool. Sorry, made a mistake there. Yeah, when you cross multiply, it'll be I secondary times number of turns in the secondary divided by primary voltage, primary current times the number of primary turns. Cool. So we know our secondary current is 22.5 times 1 is 22.5. And we know assuming at the moment that we can't multiply by the primary, that's what we're trying to figure out. So we get rid of that in the equation, and then we just use the number primary. Gives us 45. So 22.5 divided by 45. Cool. Gives us 22.5 divided by 45, gives us 0.5 of an amp. So in a step-down transformer, the current is always going to be less on the primary side and more on the secondary side because you're taking a higher voltage at a lower current, stepping it down to a lower voltage at a higher current. So now we can calculate the primary phase current. So we take our formula again, IL equals square root of 3 times I phase. And we can divide the line current by the square root of 3. Giving us 0.5 divided over square root of 3, which gives us 0.29 amps in the phase. Is this making sense to everyone? Is there anyone who's lost? Yeah. Best speaker. Yeah. If anyone's struggling, don't wait for me to ask. Just put something in the chat, and then I can stop. We can go over it a few times and make sure it's making sense to you guys. Last thing I want is for me to just, yep, we're going to do a couple more. I'm going to do at least 3 examples, and then at the end, I'm going to do a more complicated one. Cool. So a transformer is connected delta-delta, and it's a 5-to-1 step-down transformer, and we know the secondary line current is 60 amps. Cool. So calculate the primary line current. Cool. So from what we were talking about before, we know that IS equals divided by IP equals NP over NS. So we can swap that round. So the I secondary. So we already know to rearrange it to I secondary times the number of turns secondary divided by I primary multiplied by the number of turns in the primary. So we know secondary line current is 60 and our secondary turns are 1. So it's still 60. And then we're trying to figure out the primary line current. So we just ignore that and we take the number of primary turns, which gives us 5. So when we do that, we get 60 divided by 5, we get 12 amps. Now we calculate the primary phase current. Cool. So we know IL equals the square root of 3 times I phase. So we take IL and divide it by the square root of 3 to give us I phase. So 12 divided by the square root of 3 gives us 6.93 amps. Okay, we'll look at another one. So transformer is connected delta-delta and is a 1 to 25 step-up transformer. and the primary line current is 120 amps. So we'll go to calculate the secondary line current. So again, we write out our formula because we know that, so we're looking at the primary line current. So IP times NP over IS times NS. Cool. So we know the primary current is 120 amps. The number of primary turns is 1 because it's a step up. So we know it's 120. We don't know the secondary current. We're trying to figure that out. But we know there's 25 turns in the secondary. Cool. So we do that. So 120 divided by 25 gives us 4.8 amps. Then we can calculate the primary phase voltage. Again, IL equals square root of 3 times I phase. IL divided by the square root of 3 gives us I phase. So 4.8 divided by the square root of 3 gives us 2.77 amps. So connection. So these are the two ways to draw the connection. So second combination we've been looking at is delta-delta. In this configuration, there is a direct conversion between phase voltages and the primary and secondary windings. Because phase and line voltages are the same, when configured in delta, then line values are also directly converted. Cool. You always want to take, so whenever you're doing this, you always use the line voltage to do your conversion, and then you use the square root of 3 to change it over. Or, for example, if you were doing a delta star and you had the phase current, when you changed it over using the conversion method of IS over I primary equals NP over NS, you would then have to take the value you get on the second side and multiply that by the square root of 3 to get your line current. And those are just the two ways you can draw it. You can draw two deltas next to each other, or you can draw the windings connection there. Cool. Another video, same guy.
Hello and welcome to this electrical principles training video. In this video, we're going to continue considering the subject of three-phase, and more specifically, we're going to look at the relationships between line voltage and line current and phase current inside a delta-connected three-phase load. So we've got our training rig ready to go. Let's bring the camera in and we'll have a little look at what we're doing. So on our simulated three-phase load here, you can see we've got three loads. Again, these loads can be used to represent perhaps the three windings of a motor. Obviously, there's some inductive effect to take care of there, but we'll look at that in a later video. And you can see that what makes this a delta connection is if we look at each individual load, you can see it's got two connections. Traditionally, we think of those as being the line and neutral connections. But here you can see that every resistor, one of the connections is connected to another side of another resistor, and the other side of that resistor is connected to the other side of that resistor, and so on and so forth. This is called a delta connection because when it's laid out in this kind of diagram form like we've got here, it looks a bit like the Greek letter delta, which is triangular in shape. But it's very important to bear in mind that, again, if you open up something like a transformer or a motor or something that has a delta connection inside it, it won't be physically laid out as a triangle. The loads will likely just be side by side next to each other or perhaps arranged around the frame of a motor. And it is the way that we connect the ends of the loads together that makes it a delta connection. So if you remember, in a previous video in this series on star-connected loads, we defined the different voltages and currents that we find inside a three-phase connected load. So we have our phase voltage, our line voltage, we have our phase current, and we have our line current. So let's just remind ourselves of those definitions because we define them in such a way that it would work for both star and delta. So the line voltage is the voltage between any two supply lines. So that means we can measure the voltage between L1 and L2, or between L1 and L3, or between L2 and L3. They will give us similar readings. We will get the line voltage. Now we define the phase voltage as being the voltage across the load. In the star-connected system, that meant measuring the voltage between line and neutral effectively. But what do you notice about this delta-connected load? What's missing? There's no neutral. The neutral isn't required in here, and in fact, there's absolutely nowhere for us to connect it up. So we defined our phase voltage as being the voltage across the load, and that's why this definition comes in so useful now, because we don't have to worry about that missing neutral. We've got here the voltage across the load, so we could measure it across here, or across here, or across here. And understanding that is going to help us to understand the relationship between line voltage and phase voltage in this delta connected system. Moving on now, we've got our line current and our phase current. So remember, the line current is still the same definition as it was before. It's the current that flows through the supply line. And you can see I've left these little loops here so I can get my clip-on ammeter over that to measure the currents. And the phase current is the current that flows through the load. So I can measure that at any one of these three loops. I can measure the current through the load, and that will give me my phase current. So now what we're going to do is we're going to power the rig up. We're going to put power onto it, and then we're going to measure those voltages and currents, and then we'll explain what the relationships between them are. Now, I need to work a little bit more quickly than usual when I'm doing this particular connection, because now we're connected in delta. These resistors get even hotter than they did in the start video. We don't want this to burst into flames live on camera. This isn't that kind of video. So here we've got our rather lovely Mega Avo 835, which we're going to use to measure the voltages in the system. So I'm going to set this to measure AC voltage. And you can see here that I've got my long, small probes connected to my test leads, which is going to allow me to access the live part in a safe fashion. Please don't attempt to recreate this at home. There's a lot of heat involved here. We're dealing with three-phase electricity, which is even more lethal than single-phase electricity. So please don't try this at home. This is being done under controlled conditions. So without further ado, we'll power up the circuit. So I'm connecting a three-phase supply to my circuit now. So current is now flowing through the system. So the first thing I'll do is I will measure the line voltage. So I measure that by connecting across here and here. Embargo in making these connectors, leave you with a nice little testing terminal in there. And if we look at the voltage on the screen there, you can see we're getting 430 volts. Now we'd expect that to be 400 volts in a three-phase system. However, we know we've got our tolerances of +10 and -6%. So we're well within that tolerance there. Now we're going to go and we're going to measure the phase voltage. So let's measure that now. I need to be a little bit careful here, so I need to get under these shrouds that are on here. And let's have a look at that. So you can see there that we're now measuring, again, 430 volts. So that's quite a nice reading that we're getting. So you can see there that the line voltage and the phase voltage inside a delta connected load are the same. Now, when you think about that logically, that actually makes quite a lot of sense. So I'll power this off now. You can see that if I measure the phase voltage across here and here, there's no difference between measuring the voltage there and measuring the voltage with my probes here and here. And likewise, there's no difference then between measuring the voltage between here and here, or here and here, or anywhere along the length of this up to this point. So you can see there that the phase voltage is the same as the line voltage. So now we're going to measure the currents inside our system, and to do that we're going to use our rather lovely Mega DCM 305E. Now this is normally used for measuring leakage current inside installations, but the value of it here is that it will measure very low currents quite accurately, which is perfect for this system because we're dealing with quite small currents. As you can see there, it's actually going to be measuring in milliamps. So that's what we're looking at here. So let's power this up. And as I've just discovered to my cost, these resistors get unbelievably hot, so I'm going to try and keep my fingers away from contact with those. But let's measure the phase current first of all. So we could measure it here, here, or down here. They will all give us the phase current, and they should all be the same. So let's measure the phase current at this point. So if I measure the phase current there, you can see there we're getting 129.4 milliamps thereabouts. So that's our phase current. So what do you think is going to happen to our line current? Do you think it'll be the same as the phase current? Do you think it will be higher? Do you think it will be lower? Well, let's take a measurement and let's find out. So if we put our ammeter over there now, you can see that we're coming out with 225.1 milliamps, 225.1 milliamps. So we're actually getting a higher current here than we have over here. Now that kind of makes sense because the current flowing through this line conductor isn't just the current flowing through this load, it's also part of the current flowing through this load. So these currents combine to give us the value here. But as you can probably see from those two numbers that we just measured, it's not a matter of just adding those two values together. We can't just double this value to get that value. There is a number that relates them to each other. And if you've already seen the start video, hopefully you know what that number is. So at this point, we're going to go over to the whiteboard. We'll have a look at a diagram of this, and we'll have a look at those all-important relationships between voltages and currents inside a delta connected load.
So you can see on the screen here, we've got our delta connected load drawn out. And what we can do now is we can fill in our individual voltages and current.
Cool. So that's mostly just doing what we were looking at before, doing the calculations. Cool. So star delta configured transformer will typically result in the secondary side have a lowered effect on step-up transformers and increased effect on step-down transformers that when the turns ratio would initially indicate. Delta star configuration has the opposite effect as the previously mentioned configuration. Cool. So some hazards to remember. So one key factor to take into account is when direct conversion occurs, there is a 30-degree phase displacement between the primary and secondary phases. This is not an issue in an independent system as the primary and secondary circuits would never be connected. However, in a wider scheme of things, it can be potentially dangerous if star delta conversion occurs into a system that has had other configuration methods and other transformers utilized. It can cause a difference between these parallel circuits and circulating currents will flow in the system. A common relationship used in New Zealand's Delta Star transformer is DY11. This is where the circuit configuration is laid out on a clock face. The points of the triangle in the primary delta configuration is at the top of the clock, 12 o'clock, when the tip of a star winding is placed at 11 o'clock. This represents the 30-degree phase displacement between the primary and secondary windings in this configuration. So the first and last transformer, usually in a transmission system, will be a delta star at the consumer end and a star delta at the generation end. And for the most part, throughout the network, it will always be delta delta, which reduces the need for the neutral or star point. What is this last video?
Hello and welcome to this electrical principles training video. This video is designed to be used in conjunction with the worksheet that you'll find the link to in the description below. So if you haven't already done so, please click that link, download the worksheet, and then follow through the questions as we go. Have a go at answering them yourselves and then check your answers against the worked example that I'll show you on the board. So let's get started by answering question 1. So question 1 tells us that 3 identical resistive loads of 25 ohms are connected in star to a 415 volt supply. And we're asked to...
Okay, so this is something we can revisit next week. For now, cool. So we will work on this. So we've got a delta star transformer. It's 25 to 1 step down. We know our primary voltage line is 10 kV, and then we know that our line voltage on the primary is 2.4 amps. Cool. So now we will work out voltage phase. So we know because it is a delta, it's basically parallel, we know that voltage is the same. So we can take our phase voltage and we can fill that in. So 10 kV. Cool. So we know our I line. Cool. But then we need to work out our I phase. So to work out our I phase, we know that I phase will equal I line divided by square root of 3, which means it's 2.4 divided by square root of 3. Cool. What have you guys got? Yeah. Okay, guys. So we need to remember with our rounding, anything 4 or below, you round down. Anything 5 or up, you round up. So normally, they want your answers to questions in 2 decimal places. So we would go 1.39 amps because it ends up being 1.3856406. If we were to go to 3 decimal places, it would be 386. Because you would round the 6 before the 5 up, making 386. So then we can take that and we can put that into our sheet. 39, very out of the room. Okay. Cool. So we know our phase. So now we need to figure out our line voltage on the secondary side. So we know VP over VS equals NP over NS. Cool. So we know that we need to cross multiply when we're doing fractions. So it equals voltage primary times number of turns on the secondary over voltage secondary times the number of turns on the primary. Cool. So we know that we're trying to find VS. So in actual fact, it ends up being, when we actually want to write this out, VS equals VP times NS divided by NP. And we know that the voltage primary is 10,000. The number of the secondary is 1. And we know that it's 25 on the secondary for the turns. So it's basically, we get rid of this because it's just 1. It's 10,000 divided by 25. So that gives us watt as our, just the camera. That gives us watt as our voltage secondary. Sorry, VL secondary. Yeah, pretty much gives us standard 3-phase voltage of 400 volts. Cool, so we can take that and add that into our table, 400 volts. Cool, so then we can work out our voltage phase. So we know VL equals square root of 3 times V phase, and we know we can rewrite this calculation, so it's V phase equals VL over square root 3, which, considering this is I think you may have made a miscalculation there, Ben. Yeah. Yeah, it should spit out 230.9 or, yeah, 230.94 volts, which, yeah, basically if you look at the 400 volts, you go, yeah, cool, 230. Yeah, easy. So just for ease of fitting it in, we will put 230 volts there. Yeah, 230.94 is the more accurate one. Cool, so now we need to work out our I line. Cool, so we know our I primary over I secondary is equivalent to NS over NP because it's an inverse relationship. And then of course we need to cross multiply. So it's IP times NP over IS times NS. Cool. So we know the I primary is, and we're trying to figure out I secondary, so we can get rid of the I secondary. Cool. So we take our I primary, which is our 20 is 2.4, and we multiply that by the number of turns, 25. Okay, there's no point dividing by the number of secondary turns because it's 1. So we know it's just 2.4 times 25. So 2.4 times 25 gives us, someone was doing, Ben, were you doing the current? Yeah, gives us 60 amps. And what's our I phase? We don't need to do any calculations for our I phase, do we? Because we know in a star configuration, it is 60 amps because it's the same. That makes it look like I drew a 69. I did not draw a 69. All right. Cool. So this time we have a star delta transformer. It has a 1 to 50 step up. Cool. So on the primary side and the secondary. So on the secondary side, we have our V line. 55 kV. On our primary side, I line is 25 amps. Hold on. Drew those a bit too close together. So we have a I line, 25 amps. We have a I phase. Cool. So the easiest way for us to work out values here is to figure out what we know about our relationship. So we know on the secondary side, it is a delta. So we know in delta, our V line and our V phase are going to be the same. So the first thing we do, input 55 kV. And then we also know that on our primary side, because it is a star, the current stays the same. So we know we can fill in our I phase as 25 amps. But now we have to figure out our primary line current. So we go back to the trusted formula. So we'll just put voltage secondary on the top, voltage primary equals number of turns secondary over number of turns in the primary. Cool, so we can cross multiply. So voltage secondary, numbers primary, voltage primary over numbers secondary. So we can take our voltage secondary, multiply it by the number of turns in the primary, so the number in the primary. We can divide that by the voltage primary times the number of secondary. Cool. So the voltage secondary, so we know that is 55,000 times the number of primary, 1, so we can ignore it, over voltage primary. We don't know, we're trying to figure that out. So we divide it by the number of turns in the secondary, which is 50. So we divide 55,000 by 50, we get what? Right, we get 1100 volts or 1.1 kV. So we can take that for our voltage line. We can put that in 1.1 kV. But now we need to figure out our phase voltage. So we know that the VL is equal to V phase times square root of 3. And we can rearrange it so that V phase is equal to VL divided by the square root of 3. So we know that is going to be 1100 divided by the square root of 3, which gives us what? I think you've got one too many zeros there, Ollie. Just check the way you've done the math. Maybe you've put one extra zero. Maybe you put 11,000 instead of 1100. Yeah, so yeah, it gives us 635.085. So we round to 0 0.09 volts. So we can put that into our table, 635.09 volts. Cool. So now we need to work out the secondary currents. There is another way to do this. I'll quickly give it to you. So you take 1100 multiplied by 25, which is our line current, divided by 55. Cool. So if we do that, we get we get 2,7,500 divided by 55,000. This gives us 0.5 amps. Cool. Now, just to double check that that's correct, what we're going to do is obviously because we have I secondary over I primary equals NP over NS cross multiply. We've got I primary times N primary over IP times IS, sorry, bad, IS times NS. Cool, so we know we're trying to figure out I secondary, so we can get rid of that. So we just have NS. So I primary 25 times 1, it's not going to make a difference, divided by 50, which gives us 0.5 amps. So there's more than one way of working it out. We can do this using the number of turns, but if we don't have the number of turns and we have the primary voltage and we have the primary current and the secondary voltage, we can figure out the secondary current just because we have, basically we're working out the power. Excluding losses, we're just using the power in this formula to figure out the answer. So we know the line, and this is the line because I used the line voltage and the line current of the primary and the line current of the secondary to work this out. We know that it's 0.5 amps, but also we know that IL and I phase and delta are different. We then have to figure out the phase current. So we can then take our line equals I phase times square root of 3. So therefore, I phase is equivalent to IL divided by square root of 3. So it's 0.5 divided by the square root of 3, which gives us what? Yep, pretty much gives us 0.29 amps. We can take that and fill it in. And there we have our primary and secondary phases and currents, voltages and currents. And obviously, if we had our losses, we could start to add them in once we figure out our power. Just remember that you guys have done AC theory and power factor. So if you guys remember back to your AC theory, power factor, I'm pretty sure you guys should have done that already. It's all the power relationships are always the triangle relationship where you've got your power here, you've got your reactive power here, Q, and you've got your actual power, S. So this is remember, this is the actual usable power of a transformer. This is the resulting losses because of the inductance in the windings. And then this is the apparent power, which you're actually paying for. Okay, guys. So, yeah. Thank you for joining in. Good lesson. If anyone's got any questions, feel free. The best way to practice this stuff is just take the common power voltage levels you have in distribution transformers. For example, 11, 1.1, 55 kV, 220 kV, practice doing star, star, delta, 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 star, and then just input your own numbers.